All right, welcome everyone. I am going to make myself a little smaller here. Try to stay out of the road of the video of the screen. So today I want to talk to you about the similarities and mostly the differences of mass and weight, even though we use them interchangeably. Many of you have probably stepped on a set of scales and said, "How much do I weigh?" Well, was that really weight or was that actually mass? When we are actually using one of the in chemistry class or in biology, and we were weighing out a substance using one of the pan balances, we should have actually said you are massing the object because you are measuring something in grams or kilograms, which we'll know that is a mass. Weight, we will learn is a little bit different. It's more of a calculated, derived equation where mass is just how much of something you have. So I'm going to start today with a couple of cartoons, and I'm not going to say a whole lot about these. I'm going to, because it's a little small, I'm going to read what each of these characters are saying about. This one is about weight. And this person here says, adding air won't affect the affect. Let me start again. Adding air won't affect the weight of the ball. Air is just empty space. The person in the yellow shirt says, if you add air, the ball will weigh more because air is made of atoms and they have mass. Girl here in the red says, adding air to my ball will help it bounce higher because it will be lighter. Air makes things lose weight. And then finally, this last one says, what do you think? And this was actually created by a science teacher on a test I was reading. And so she wanted to see what her students thought about these three characters. So we'll come back to this. Maybe one or all or none are actually accurate. The next slide. This one is actually about gravity. I don't think it was probably made for the same reason. But I'll start down here in the bottom left-hand side. This person says, gravity pulls on things on Earth, but not in space. Astronauts float. This next one says, gravity pulls things to the center of the Earth. Center is spelled correctly if you're in England. Person over here in the, looks like kind of the flannel. Gravity only pulls on things that are falling. Gravity only pulls on things that are falling. We've got the, I just got the little apple and the whole thing with Newton, right? And finally, this person at the bottom, gravity pulls on things and makes them fall down. So, any all, maybe none of them, maybe all of them have a bit of truth. So, just some food for thought, and we'll perhaps come back to those later in the presentation. So, to our targets for today. So, hopefully, when we're done today, you will be able to differentiate between mass and weight and some aspects of each of those. Also, being able to apply Newton's second law to determine unknown variables. So, we'll see that. We've actually seen Newton's second law when we were figuring out like how fast our potato gun fired, how much acceleration the potato felt through the gun. We're actually using Newton's second law. So, we're going to use that in reference to weight today. So we have this graphic here, and there's anything you feel that you should write down, please do. And this does a pretty nice job. It's actually over there. It's backwards for me. So mass is measured in kilograms, grams, even pounds that are the English form of mass, even though when we step on a scale and it measures pounds, we're actually doing it because it's a force. Whereas weight is measured in newtons. So we named it after Newton since Newton was the one who kind of proposed this idea of gravity and that the Earth is going to pull things to its center. It's going to pull, so to speak, things to its center. Mass always remains the same, and that is true. It doesn't matter where we go. If I have a 1 kilogram block of iron, it's going to have that same mass no matter where I take it. If I take it to Mars, it's still that same block that has a mass of 1 kilogram. Whereas weight does change with location. So if I take that 1 kilogram mass on Earth, which is 10 newtons, and I take it to the moon, it's going to have less weight. It'll have the same mass because it's still the same block. It's the same stuff. It's the same matter, but it's going to have a different force of weight then. Mass is closely related to inertia. Now, inertia, you've talked about Newton's first law. Newton's first law says that an object at rest wants to stay at rest. An object in motion wants to stay in motion. So if Mr. Acker comes over here and he applies a force, he's going to keep rolling. So that object that wanted to keep rolling, it wanted to keep in motion. Now I slowed down because there was an opposing force with friction. Now, if I just sit right here and I wait, and let's see, if I do nothing, I'm going to stay here. There's no force being applied to me. Well, actually, there is. There's a force being applied down. Why am I not going down? Because there's also a force pushing up. Newton's third law. But the idea that inertia, the heavier an object is, the more mass it has, the more inertia it also has. And we also think of inertia for a moving object. We think about momentum. And we'll talk about that later. We'll do some calculations of momentum and talk about how that's conserved, especially when two objects run into each other. A really massive object runs into a really light object. Pretty cool things happen. Well, I guess it depends if you're the light object. And then, whereas weight is going to depend on gravity, and it's directly related. It's directly proportional, meaning if I double gravity, I double weight. If I triple gravity, I triple weight. W-E-I-G-H-T, not like wait for it, the other kind of weight. If I have it, H-A-L-V-E-S, if I cut it in half, if I cut the gravity in half, then the force of weight will cut in half. The reason the astronauts were able to jump really high on the moon is because they had less weight. They had the same mass, but they had less weight. So whatever strength they had on Earth, they took the same strength there, they could jump a lot higher. It also looked like things were in slow motion in the moon because things did actually fall slower. And it was actually easier for them when they were on the moon to kind of hop around. So they just hopped a little. It would actually go further because they would have an initial Vx and gravity was pulling them down less. So they'd actually go further than hopping on Earth. They had to be careful. And actually, the way they trained was a lot of times in water, underwater, actually, because water would give them that buoyancy that kind of represented the moon. But I am off on a tangent here. Let me pull the reins back. We don't actually measure mass directly, the amount of stuff. We can kind of work backwards once we have newtons, but we cannot measure it directly. We can see it, and we could describe it in different ways. We could say how much space it takes up. We could do a volume. We can do kind of have a density of this, and that helps us figure out the volume that it takes up. But we don't actually, the whole idea of a kilogram or a gram is just another comparison. So if something has a mass of 1 gram, which is about a paperclip, then that's a cubic centimeter of water. We're just comparing. Whereas weight, we can directly measure that using a scale, using a force sensor. I like this graphic down here on the bottom left. That was kind of interesting. It says my weight on Earth is 560 newtons. On the moon, I have a weight of 90 newtons. Now, why is it less? Because there's less gravity. But no matter where I go, I have a mass of 56 kilograms. Now, the idea is kind of a conversion here. If you're trying to go from kilograms to pounds, if you take kilograms, you multiply by 2.2, you kind of double it. That gives you about the mass. So this person has a mass of a little over 112 pounds. That's a kind of quick conversions. 2.2 is the actual amount. Hey, it's time to go home, but I'm going to keep talking here. Now, let's see. So I'm going to ask you a series of questions before we actually move on about kind of the difference between mass and weight, and then I'll be back with a little more content. All right, so I'm back and I'm going to talk a little about quantifying our weight or calculating our weight. If somebody says quantify, we're calculating. And so the weight is a force. It's the force that the Earth or that the moon or the gravity is pulling down in a way. And we don't really actually know why this happens. There's some theories. We actually think that really early on in the Big Bang, nothing had actual mass or didn't actually have weight. So there wasn't gravity, but then there was some sort of a wave that things passed through, and they was magically given this force that caused mass to be attracted. And you can do some YouTube videos on gravity waves, and it's kind of an interesting kind of over my head sometimes. But we're going to use this equation. You've seen this. Force is mg, or force equals mass times acceleration. Gravity is an acceleration, so we did F equals ma. If you remember when we were doing our F equals, sorry, I can't write very well using my little clicky thing here. Not particularly good to write on. We're saying F sub W, force of weight, is equal to the mass times the value of gravity wherever you are. So this should look familiar to you. Now, I pull up this next chart, and you actually have this. I've given this to you. Let me get me way out of the road. I'm going to have a hard time getting, I'll come down here. And this has some interesting information on it. Mostly why I wanted you to have it is so you can see the values of gravity here. You have those for quick reference. The density is actually quite interesting to think about a little bit. This is the density of the different planets, including Pluto, which is actually a dwarf planet because it's super small. In fact, if you look at the size of Pluto, if you look at our moon, so our moon has a diameter of, where are we here? 3,500 approximately kilometers. The moon, the Pluto, is actually 2/3 of the size. Well, it's a third smaller. So if it's about 2/3 of the size, it's pretty small. Now, it's not really the small that makes it a dwarf planet, although that does have an effect. It also has a weird orbit. Sometimes Pluto is closer to Earth, to the sun than Neptune is. And plus, it's off kilter. So all the planets actually go orbit in a flat plane, where Pluto's orbit is actually a little bit like this. So it orbits a little differently. It was probably captured. It was probably a rogue space rock that actually got captured by our sun and just stayed in our orbit. Now, density, I think, is really fascinating. The densities here, the unit they're giving in, water would have a density of 1,000 kilograms per cubic meter. So if you took a cubic meter of water, so you've been meter stick by meter stick by meter stick, that would be exactly 1,000 kilograms. If you actually look, so Mercury, if we had a giant like ocean and we put Mercury in that, neglected it was really big, really big, obviously, it would sink, as would Venus, as would Earth. And actually, Earth is pretty dense. If you actually think about it, if you compare all these, Earth has the biggest density, which I don't know if that's important or not, but it's the most dense of anything. Interesting. The moon, Mars and moon are pretty close in density. Jupiter begins the gas giant. So we usually think of the gaseous. Well, gaseous we usually think of being like really light and not very dense. Well, it's still pretty stinking dense. In fact, it's dense that it would still sink. So even though it's a gas giant, the gases would be dense enough. So condensed because of the pressure and whatnot, it would actually sink. However, Saturn would actually float in an ocean of water, which is kind of interesting. And same thing with Uranus. Uranus is not actually a gas giant, whereas Jupiter and Saturn were the gas giants. I don't think technically it is a gas giant. Then you have Neptune and Neptune, again, pretty far out there. Uranus is the one that has it actually orbits. It doesn't spin this way. It actually spins the other way. So its axis north and south pole have actually kind of turned sideways. Anyhow, not that important. Just trivia. Gravity. I do want you to have these gravity values, and we'll continue to use these values and presume that they're exact as a working problem. So even Earth at 9.8, I know we've been using 9.81. Let's use 9.8 for this. Okay, unless you're told otherwise. Okay. So now you're going to have a series of questions that are going to ask you to apply the force of weight mg a couple different ways. And so work the problems. You're going to actually see the problem. Then there'll be a place for you to respond, and then you'll see the answer key. So I've worked all these problems. I won't have any more video of this. You can just see my key, and I'm going to guess you'll figure out. If you missed it, you'll figure out how you might have missed it. So they're pretty straightforward. Obviously the equation is pretty straightforward how to apply. So it's just a matter of getting your variables right and figuring out which planet you're on and reading carefully. So, all right, thanks so much. I'll see you next time. Thanks for doing this exercise.